This is the second part of a Level 2 Functional Skills Maths paper from NCFE. In this part you can use a calculator. And one thing I want to draw your attention to before we move on to look at the questions is this, which says use pi equals 3.14. So if we have any questions related to circles, we've got to use this. Activity 2, pollution. Ali sees an article about the health risks from pollution caused by cars and other vehicles. The article states that every year 970,215 working days are lost due to air pollution related illness. Write 970,215 as a number. So 970,000. So we know we've got 3 more digits to follow. 215. So this is the number. 84% of the days lost due to air pollution related illness are due to breathing related problems. Calculate days lost due to breathing related problems. Give your answer to the nearest thousand. So it's 84% of 970,215. As we can use a calculator, we're going to go 84 out of 100, because that's what 84% means, of 970,215. So plugging this into the calculator, we get 814,980.6 days. We've got to give our answer to the nearest thousand. So looking at the digits locating units, tens, hundreds, thousands. So this is the digit to round. Do we round it down or up? We look at the digit on the right of 4, which is 9. And that means we've got to round the 4 up, because this is higher than 5. So we're going to make the 4 a 5. The digits after will become zeros. Digits before will stay the same. So we've got 815,000. Schools and colleges can have very high levels of air pollution if they are close to a main road. This is a map of the area around Alice College. At its closest point, the main road is 0.35 kilometers from the college. So this is the closest point, which is also 7 centimeters on the map. What scale has been used for this map? Give your answer in the form of 1 to n. Now, if you look at the form that this has been given in, we haven't got any units. So that means in our answer, we'll have to work it out for the same units. So we've got centimeters here, and I'm going to keep it as centimeters also for the distance on the ground. So let's work it out. So 7 centimeters on the map is equal to 0.35 kilometers on the ground. Let's simplify this and work out what 1 centimeter on the map is equal to. So as I said earlier, I want to convert this into centimeters because I want to use centimeters as a unit for both the measurement on the map and on the ground. So 0.35 kilometers. We know that in 1 kilometer there are 1,000 meters. And if you've forgotten that, the K gives you a clue. K meters. So what about 0.35 kilometers? How many meters is that equal to? Okay, so to get from 1 to 0.35, we multiply by 0.35 because any number multiplied by 1 gives the number itself. So we'll do the same on the other side, which is going to give us 350. And it does sound right because if 1 kilometer is equal to 1,000, 0.35 kilometers will be equal to less. So that is 350 meters. We've got the same units on the same side. Now let's convert this into centimeters. So 1 meter is equal to 100 centimeters. Again, centi, like century, there are 100 years in a century, 100 cents in a euro, that sort of thing can help you remember. What about 350 meters? What's that equal to in terms of centimeters? So to get from 1 to 350, we multiply by 350, and we'll do the same on the other side, so multiply by 350. And that means 350 and adding the 2 zeros. So that is 35,000 centimeters. So 7 centimeters on the map is equal to 35,000 centimeters on the ground. So I'll replace this now with the centimeters. Now, if 7 centimeters are equal to 35 centimeters on the ground, what about 1 centimeter? To get from 7 to 1, we divide by 7, because 7 divided by 7 gives us 1, and we do the same on the other side. So 35,000 divided by 7 gives us 5,000 centimeters. And as we said before, when we've got the same unit used in the scale, we just write the numbers down. We don't need to include the units. So this would be 1 to 5,000. And that's the form we're after looking at the question. Some students drive or get a lift by car to and from college. Ali wants to encourage students to travel to college by other methods of transport. He conducts a survey to find out how students travel to college. This table shows his results. Method of transport to college: walk, number of students 52, car 36, bus 28, and cycle 4. What fraction of the students travel to college by car? Give your answer in its simplest form. So by car, we've got 36 of them out of the total, which is 120. We've got to write this in the simplest form. So as you can see, we can divide this by 6. So that would be 6, and this would be 20. And we can divide this even further, divide by 2 to get 3. over 10. So 3/10 is the answer. And you could have chosen a different route, maybe divided 36 and 120 by 2 first and then by 3. So whichever way, as long as you get to 3/10, it should be fine. Ali wants to find out how much pollution is produced by students traveling between home and college by car. He asked the students that travel to college by car how far they live from the college. The students attend college on 164 days per year. This table shows his results. Ali finds this conversion graph. The average fuel consumption of a car is 38 miles per gallon. A typical car produces 2.44 grams of nitrogen dioxide per litre of petrol used. Ali uses the estimated mean distance to calculate the average amount of NO2 produced. Calculate the average amount of NO2 produced by a student who travels by car to and from college for 164 days. So let's work out the mean distance from home to college in kilometers first. So we've got 0 kilometers to 1 kilometer. The midpoint, because that's a range, midpoint that we're going to use is 0.5, so halfway between 0 and 1. And there are 13 students doing that sort of distance, so we're going to multiply and it gives us 6.5. Now between 1 and 2 we've got 1.5, so multiplied by 11 gives us 16.5. Between 2 and 3 we get 2.5 times 7, 17.5. Between 3 and 4 we get 3.5 times 5 gives us 17.5. So adding all of these together gives us 58, which we're going to divide by the number of students in total. And that is 36. So 58 divided by 36 will give us the estimated mean of kilometers. So that is the distance from home to college, but they will come back as well, return home. So that means we need to double this. So 2 times 1.61 gives us 3.22 kilometers. So that's for one day. But in fact, there are 164 days. So 3.22 times 164 gives us 528.08 kilometers per year. Now looking at this, it says the average fuel consumption of a car is 38 miles per gallon. So let's have a look. 38 miles per gallon on the graph. It's going to give us about 13.5 kilometers per litre. So if I divide 528.08 by 13.5, it should give me how many litres per student are needed, which is 39.117 litres. Now, finally, let's work out how much nitrogen dioxide that produces. And we've been told that it's 2.44 grams per litre of petrol used. So we'll do 2.44 times the 39.117, which is equal to 95.44548 grams. So we'll write that as a final answer. Air pollution can affect the lungs. Research shows that for school-age children, exposure to nitrogen dioxide is associated with reduced growth in lung volume. This scatter diagram shows the results of a study into lung capacity. The level of NO2 around Alice College is typically 55 micrograms per cubic meter. Estimate the additional lung capacity that children would gain over a period of 8 years if the pollution level were to be reduced from 55 to 35 micrograms of NO2 per cubic meter. Give your answer as a fraction of a litre. Okay, so increase in lung capacity over a period of 8 years in litres. And we're going from 55 to 35. But the first thing we need to do is to draw a line of best fit and then estimate. We're going through dots, trying to keep an equal distance between dots on both sides. So let's go up to 55 which is about 1.31. Again, we estimate this, we don't need to be really exact and accurate here. And then 35, so going up, it gives us 1.35. So working out the difference between 1.35 and 1.31. .04, which is 4 out of 100. If you're confused by this, just imagine if this was money you'd be 4 pence out of 100 there are in a pound. So 4/100 is the answer. If your estimate was slightly different, maybe 3/100 or 2/100 or 1/100 or 5/100, that should be fine. Activity 3, boxes of chocolate. Kate works for a chocolate company. Her job is to supervise the packing chocolates into boxes. She sets up the computer to print the labels for the boxes. The label needs to be a 6 centimeter by 5 centimeter rectangle. She needs to program the computer with the coordinates of the corners of the label. A is one corner of the label. Each square represents 1 centimeter squared. Draw one possible position for the label on the grid and write the coordinates of each corner. So there is A. We could go and do this 1, 2, 3, 4, 5, 6. And going 5 down because it's got to be 6 by 5 centimeters. 1, 2, 3, 4, 5. And then of course 6 this way and 5 this way. Let's just label them. So B, C and D. And we'll need to write the coordinates on the grid as the question asked. So for point A, this is starting with the x coordinate, that is -2, and going to y, that is 3. So -2, 3. For B, this is 4, going up to 3, so 3. For C, this is 4, -2. For D, this is -2, -2. This is a diagram of a box to be filled with chocolates. The box is a cylinder. The diameter of the box is 11 centimeters and the height is 22 centimeters. Calculate the volume of the box. So we've got to use pi is equal to 3.14. So the volume is worked out by multiplying the area of the base, which is the same as the area of the top here, by the height, which is 22 centimeters. So let's work out the area of the base, which is pi r squared. So that is pi 3.14 times the radius is half the diameter, so that would be 5.5 squared. So this is 3.14 times 30.25, which is equal to 94.985. So we've got the area of the base. Now we're going to multiply it by the height. So we're going to do 94.985 times 22 gives us 2089.67 centimeters cubed. The boxes are filled with chocolates and weighed. The target weight of each full box is 294 grams. The box is automatically rejected if it's less than 98% of the target weight. Kate looks at the weights of 10 boxes of chocolates. Use this data to estimate the probability that the next 2 boxes will be rejected. Show your answer as a percentage. So first of all, we need to find out 98% of 294 so that we can see then which of these are under that weight. So we're going to do 98%, which is 98 out of 100 of 294. So in the calculator, we get 288.12 grams. So that's the minimum weight. Looking at these, which ones of these are under 288.12? This one is not, this one is under, and this one is under, this one is not, this one is not, this one is not, this one is not, this one is under, this one is not, and this one is not. So that is 1, 2, 3 of them out of the 10. So this is the probability of one of the boxes, or one box being rejected. The question is to estimate the probability that the next 2 boxes, so one is rejected and the next one is rejected as well. So that means multiplying by 3/10 again. So one box is rejected and the next box is rejected. So we know that when it's and, it means we multiply. So multiplying these 2 fractions, we get 9 over 100, 9 hundredths, which is, as a percentage, that is 9%. Kate monitors the performance of the chocolate packing machine. Using plus and minus, complete the table showing the difference between the target weight of 294 grams and the next 3 box weights. So looking at the first one, that is 294.04, which means it's higher than 294. So it's a plus. But what is the difference? So we're going to do 294.4, take away 294, and that leaves us with 0.04. 293.71 is smaller than 294, so that means negative. We're going to do in the calculator 294 take away 293.71, and that gives us 0.29. The next one, 292.59, is also a negative one, so we're going to put in the calculator 294 take away 292.59, and that gives us 1.41. Kate must check that chocolates are distributed in the boxes in the correct proportions. There are 4 types of chocolate: mint, caramel, fudge, and toffee. The types of chocolate are produced in the ratio of 2 to 3 to 3 to 1. She opens a box that contains 27 chocolates in total. 8 of them are fudge chocolates. Kate thinks that the box contains the correct number of fudge chocolates. Is she right? Explain your answer. So looking at the ratio, we've got 2 to 3 to 3 to 1. 2 represents mint, 3 caramel, and then 3 fudge, and then toffee. Adding them together, we get 2 and 3 and 3 and 1, which equals 9, so 9 units. Now she opens a box that contains 27 chocolates in total. So under the total, I'm going to put 27. To get from 9 to 27, we've multiplied by 3. So to keep the same proportion, we need to multiply each of these units of the chocolates by 3. Looking at fudge, we need to multiply it by 3. So 3 times 3 is 9. So 9 fudge chocolates would be needed. But in fact, there were 8. So is she right? No, she's not. Kate checks the number of boxes of chocolates produced each hour. The table shows the number of boxes produced over the last 24 hours. What is the mode of the number of boxes of chocolate produced per hour? So mode is the most common number. 1494. There is 1 here. We've got 1 here, 1 here, 1 here. Yeah. Looking at 1522, there is 1 here. So just 2 of them. Looking at 1513, there are no more of it. 1498, got 1, 2, 3 of them. 1521, there is just 1 of them. 1473, we've got 2 of them. 1502, there is just 1, and so on. So basically we can see the pattern. The number that occurs mostly is 1494. Kate needs to show how the boxes of chocolates will be packed. She needs to fit as many boxes of chocolate as possible into the delivery box. This is the delivery box. What's the maximum number of boxes of chocolates that can be packed into the delivery box? And then in the second part, you'll have to explain your answer by drawing a sketch of the plan view elevation of side A to show how the boxes of chocolate will be packed into the delivery box. So what I suggest is that we do this part first because it's going to give us the answer to the first part. Let's have a look at the dimensions. So here is the delivery box, and at the top it looks like a rectangle. So the dimensions are 55 centimeter by 55, so it is a square at the top. Now let's have a look at the dimensions of the chocolate box, and it is 11 centimeters the diameter. So, and this doesn't need to be to scale. So if we think of this length being 55 and this one here, which is equal to the diameter, is 11. So how many 11s fit into 55? That would be exactly 5. So we'd be able to fit exactly 5 of them. This is not going to be perfect, and it's perfectly fine if not. So I should have made them slightly smaller. Just to give the idea. And to show that 5 of them fit across. So one more. As this is a square-shaped box, and the dimensions of both of these two items will be the same, that means we can fit 5 again alongside the width. We'll adjust the box so that we've got all of them fit in. So that we have it complete. So it's 5 by 5, so 25 in one row. Let's see how many rows there will be in total, and the elevation of side A will show us that. So looking at the side A, we've got dimensions 48 by 55. And the dimensions of the box of chocolates 11 by 22. So this is equal to 48 centimeters. How many 22s can fit in there? That would be 2 of them. So that's what I'm going to try and show. So maybe back here, that would be the box of chocolates. Same width, okay. So put 1, 2, 3, 4, 5 of them. And we can fit one more row because 22 and 22 makes 44. Again, this is not perfect and not drawn to scale, and it's all fine. So to answer the question that we had in part 1, if 25 can fit in one row, then 2 rows means 50 boxes. Kyle is training to run a half marathon. On his next training run, Kyle wants to run 5 kilometers. He plans a route in the park. He starts at point A, then takes a right turn at point B. When he reaches point C, he stops for a rest. At point C, he continues to run in a straight line in the same direction until he has completed the full 5 kilometers. The scale of this plan is 1 to 40,000. Show where Kyle finishes his run by accurately placing point D on the plan. So the distance he's going to be running is 5 kilometers. We know that the scale that's been used on the graph is 1 to 40,000. So this would be on the map or graph, and this would be in reality on the ground. As we're not given a unit, that means whatever unit we use here, we're going to use here as well. And if you noticed, the dimensions of each square are 1 centimeter by 1 centimeter. So we're using centimeters. So 1 centimeter on the map will be equal to 40 centimeters in reality or on the ground. What we need to get to is 5 kilometers. I'm going to convert that into centimeters and plug it in here so we can work out how many centimeters the whole journey should be represented on the map or on the graph. So the 5 kilometers, let's convert them to meters first. So 1 kilometer is equal to 1,000 meters. So 5 kilometers will be equal to 5,000 meters. Now to centimeters. So 1 meter is equal to 100 centimeters. 5,000 meters will be equal to 500,000 centimeters. So how many centimeters will that be shown in the graph? What do we do to 40,000 to get 500,000? So 500,000 divided by 40,000. And that gives us 12.5 centimeters. So the whole journey should be 12.5 centimeters. We've got 1 here, 2, 3, 4, 5, 6, 7, 8, 9. So we'll continue 10, 11, 12.5. And we'll mark this with D. It took Kyle 45 minutes to complete the 5-kilometer run. This time was 5% longer than his previous time. How long did Kyle take to run his previous 5-kilometer run? Show your answer to 2 decimal places. So if we think of the previous duration as the 100% duration, that means now the new duration or the new length of time will be 5% extra on top of the 100%. So you'd be 105%. And that is equal to 45 minutes. So 45 minutes is equal to 105%. What we need to work out is what is the 100% amount. What's the original? So what we're going to do is divide the 45 by 105 so that we get only 1%, and then multiply it by 100 to get the 100% amount. So 45 divided by 105 times 100, which gives us 42.857142. So we'll round this now to 2 decimal places. That means we need to get rid of the digits after the 5. Looking at 7 means that we need to round this up. So 5 will become a 6, 8, 42.86. Kyle thinks that the outside temperature affects his running speed. He collects some information on the days he has completed a 5-kilometer run. Produce the scatter diagram to show Kyle's data. So we'll show time horizontally and temperature vertically. Let's have a look at the numbers. So in terms of temperature, the lowest one is 6 degrees Celsius and the highest is 25. And in terms of minutes, the lowest is 35, the highest is 52. So we've got these big and small squares as well. If we're going to show the minutes here, and they range from 35 to 52. We can show them from 30 to 55. So if we start with 30 to 35 here, 40, 45, 50, and then 55, 60, 65. In terms of temperature, they range from 6 to 25. So I'm going to start from 0 and then go to 25. We go 5, 10, 15, 20, and 25. That should work. So we'll label this as temperature in degrees Celsius. Drawing the axis. So when the temperature was 17 degrees Celsius, it took 46 minutes. 45 is here, 46 would be here. When temperature is 12, it took 38 minutes. So 36, 37, 38. When temperature was 25, it took 52 minutes. So on this line, going to 52. So there is 50, 51, 52. Nine, 36. 10, 37. 22, 50. 635. So as we can see, there is a positive correlation. We can show that with a line of best fit quickly. So about here. So the question was to produce a scatter diagram to show the data, and we've just done that. Use your scatter diagram in 4C. Kyle wants to calculate his likely time to run the half marathon. The half marathon is 13.1 miles long. 1 mile is equal to 1.6 kilometers. The forecast temperature for the race day is 15 degrees Celsius. This is a formula used to predict the time in minutes it will take to run a race based on the times achieved for a 5-kilometer run, where d is the distance and t is time to run 5 kilometers in minutes. Calculate the predicted time for Kyle's half marathon. Show your working. So we'll have a look first at the scatter diagram to work out how long it will take to run when the temperature is 15 degrees Celsius. So 15 degrees Celsius going down with 41, 42, about 43 minutes. We'll now use this to work out the answer using the formula as well. So d over 5 times 1.12 times t, which is the time to run the 5 kilometers, and that is 43 in this case. But what is the value of d? Because to work out the final answer, we need d. So d is distance in kilometers. We're given it in miles, but we haven't worked it out in kilometers. So 13.1 miles. 1 mile is 1.6 kilometers. So to get from 1 to 13.1, we multiply by 13.1. So we'll do the same on the other side, which gives us 20.96 kilometers. So now we can replace d with 20.96. So we'll go 20.96 divided by 5 times 1.12 times 43. And using a calculator, that gives us 201.88672. So that is about 201.89, rounded to 2 decimal places. Kyle goes to a circular athletics track for a 15-kilometer training run. 1 lap of the track is 320 meters. He runs in a clockwise direction, starting at point A. How far along the track from point A will Kyle be when he has run exactly 15 kilometers? Show your working. So the circumference of the circle, or 1 lap, is equal to 320 meters. And he's looking at doing 15 kilometers. So how many laps will be done first, and then in the last lap we'll find out how far away that is from point A, or how far along from point A. So the 15 kilometers will convert to meters. 1 kilometer is equal to 1000 meters, so 15 kilometers will be equal to 15,000 meters. So how many 320s fit into 15,000? So 15,000 divided by 320 equals 46.875 laps. So that means there are 46 full laps, which means coming back to point A at the end of the 46th lap, and then doing 0.875 off the full lap. So we'll work out what that means by multiplying by the full length of it, which is 320. And that gives us 280 meters. And that is how far along the track from point A Carl will be when he has run exactly 15 kilometers. A different runner starts at point A and stops at point B when he has run exactly 0.8 of a lap. C marks the center of the circular track. Calculate the angle marked X. So this is really 0.8 of the lap, and it will be 0.8 of the full circle. So we'll just do 0.8 times 360, and that's going to give us the angle. So 288 degrees. And this is the end of the paper.